on number 13, we have the limit as x goes to infinity of 1 plus 1 over x raised to the x. So if you plug in infinity, that's going to actually be, well, the 1 over infinity is going to be 0. So it's actually going to just be 1 to infinity. So this is one of our indeterminate forms. However, this is one of the indeterminate forms where we actually want to take the logarithm. So I want to use logs. So just like on number 12, I want to first define this as y is equal to the limit as x goes to infinity of 1 plus 1 over x raised to the x. So I'm giving it a name because later on when we have to transform it, it's going to make it easier. So I do want to take the ln of both sides. So ln of y is equal to the limit as x goes to infinity of ln 1 plus 1 over x raised to the x. And the reason why we are taking the logarithm is because it allows us to bring down the x out in front. So it's not a derivative thing, it's a logarithm thing. So ln of y is equal to the limit as x goes to infinity of x times ln of 1 plus 1 over x. So if we plug in the infinity, then we'll actually get, well, if you plug in infinity, then this is going to be infinity times 0, because 1 over infinity is 0, so that'll just be ln of 1, and ln of 1 is just 0. So if we get this form, we actually want to rewrite it. So rewrite. Okay. So I have ln of y is equal to the limit as x goes to infinity, and this is going to be ln of 1 plus 1 over x, and this is going to be all over 1 over x. So just like on number 12, instead of multiplying the ln by x, we are dividing by the reciprocal. So this is something that we algebraically can do, and we're doing it because if you plug in the limit, this is now 0. Whoops. I'm still getting used to my stylus after a week. So this is equal to 0 over 0, which is the indeterminate form that we like to deal with because we can use L'Hopital's rule on that. So if I, first I actually want to rewrite it again. So I do a lot of rewriting on these. So if we rewrite it, only slightly, this is going to be ln of y is equal to the limit as x goes to infinity of ln, I'm going to call this 1 plus x to the negative 1 all over x to the negative 1. I think it makes it a little bit easier to deal with x to the negative 1s. And then if we take the derivative of this, or I should say take L'Hopital's rule of this, and I want to go all the way back up here, then this is going to be ln of y is equal to the limit as x goes to infinity So the derivative of the numerator is going to be -1 x to the -2 all over 1 plus x to the -1. So definitely go back and look at your derivative of ln rules. And then this will be -1 x to the -2. And I am going to call this over 1. So if you rewrite this, you can actually take -1 x to the -2 and 1 plus x to the -1 times the reciprocal of that, so -1 x to the -2, and you'll see that the -1 and x to the -2 cancel out. So you're just left with 1 and 1 plus 1 over x. So this is kind of an important step. So what I have now is ln of y is equal to the limit as x goes to infinity of 1 over 1 plus 1 over x. So if we actually plug that in, then the ln of y is going to be equal to 1 over 1 plus 0, because the 1 over infinity is going to be 0. So this will be ln of y is equal to 1, and then I want to call that log base e of y is equal to 1, because I do want to transform it. So if I transform it, then e to the 1 is equal to y, or you can just say that our answer is e. So this is a very long problem, but it's also a very important problem, because if you look back at the original, we have 1 plus 1 over x raised to the x, and this is as x goes to infinity. This is equal to e, and this will kind of come up quite a bit in more calculus as you go along, or later on in math. So if you have to keep taking math classes, they kind of bring back this fact kind of a lot, and they kind of hide it or bring it up in obscure times. So it is good to remember that this is equal to e. So whenever you see this, that is equal to e, and I'll bring that back kind of a lot.